Today we will explore the interrelations between mainly two types of convergence. One is convergence in probability and another one is the convergence in L1 or convergence in mean. So basically this entire thing will be discussed in terms of a theorem which is known as mean convergence theorem. And naturally, to prove this theorem we can expect that we need maybe another theorem or another result. But the important thing is that in the last few lectures we have discussed one new concept, that is uniform integrability of a sequence of random variables. Now here this theorem actually gives us the idea that how this uniform integrability is being incorporated to prove or to explore the relationship between different types of convergences, that includes the convergence in mean. That's why it is termed as mean convergence theorem. Again, this proof also, we should be very careful about this proof as it goes, because there are certain techniques involved in this proof that might be extremely useful later on in working on any problem in probability theory, especially dealing with the limit theorems. So this theorem is a very important one. It's really a milestone in studying the limit theorems for a sequence of random variables. Now we are going to prove mean convergence theorem definition. First we should give the definition or recall the definition of uniform integrability, that is Xn is a sequence of random variables is said to be uniformly integrable or abbreviated as Ui if for fixed epsilon or for every epsilon greater than 0, epsilon is arbitrarily positive quantity, there always exists a delta greater than 0, and delta is again a very small positive quantity, such that supremum over n integration over a of modulus of xn dp is less than epsilon whenever we have probability of a less than delta. That means the set on which we are considering this integral has a very small probability, and the condition that supremum over n greater than equals to 1, expectation of mod xn less than equals to c, which is finite. Now in order to prove mean convergence theorem, let us just recall another important law, which is actually known as Kolmogorov's strong law of large numbers for IID random variables, that means independently and identically distributed random variables. So again, suppose x1, x2, xn be independently and identically distributed random variables, and we define Sn as summation xi, that means Sn by n equals to 1 by n times summation xi I equals to 1 to n. Then Kolmogorov's SLLN states that Sn by n converges to c, some constant which is less than infinity, that is finite, almost surely if and only if expectation of mod x1 less than infinity and c equals to expectation of mod x1. That means basically Sn by n converges to expectation of mod x1, and naturally this expectation of mod x1 must be less than infinity. So again if we look at this carefully, we have already proved this strong law of large number, but just recall that this is again a necessary and sufficient condition for almost sure convergence. Now first state this mean convergence theorem. Let xn be a sequence of random variables, that means they are all integrable, and xn converges to x in probability. Then the sequence xn converges in mean, that means L1 convergence, if and only if xn is uniformly integrable. That means we know that L1 convergence, that means if xn converges to x in mean or in L1, that will imply convergence in probability, just very simple application of Markov's inequality. But the converse might not be true. So the natural question arises that under what condition is it at all possible that the converse will hold? If so, fortunately the answer is yes. So if so, and what is the condition? Is there any extra condition that we really need? This extra condition is given by the uniform integrability. So, xn converges to x in probability. If it is given, then xn converges to x in L1 or in mean if and only if xn is uniformly integrable. Now, in order to prove mean convergence theorem, we have one lemma. Let us state this lemma first. This lemma states that if xn be a sequence of random variables which converges in mean, that is L1 converges to a random variable x, then expectation of mod x less than infinity. Now again, expectation of mod x less than infinity not only implies or ensures the existence of first order moment or expectation of x, but also it says that x is integrable. Now this proof is extremely simple. We know that xn converges to x in L1. This is known, which means, what is the meaning of this L1 convergence? This means that expectation of mod xn minus x, this goes to 0 as n goes to infinity. That is by the definition of L1 convergence. Now, we know that there is one thing called triangle inequality, which is used in many situations in mathematics, in probability, in statistics, everywhere. So just use this triangle inequality. We can write mod x is less than equals to mod xn plus mod of xn minus x. So taking expectation on both sides, we can immediately write expectation or splitting this mod x in this using the triangle inequality and taking expectation, we can immediately write that modulus of expectation of mod x less than equals to expectation of mod xn plus expectation of mod xn minus x. Now as n goes to infinity, expectation of mod of xn minus x goes to 0. So so naturally that proves that expectation of mod x is less than infinity. So now we will concentrate on the proof of mean convergence theorem. First, note one very important thing before going into the proof, like whether we do if part first or only if part first. One important thing to note is that the limiting random variable in this convergence is unique. How to prove this? Prove this uniqueness? As usual, if possible, let us assume that there exists another variable x prime such that xn converges to x prime in L1. Now we know that L1 converges implies probability convergence. That means xn converges to x prime in probability also. But it is already given in the theorem that xn converges to x in probability. So on one hand we know that xn converges to x in probability, on the other hand we have just assuming another random variable x prime and assuming xn converges to x prime in L1, we can immediately say that xn converges to x prime in probability. So this implies that capital X equals to capital X prime almost surely. That means this limiting random variable in this convergence is unique. So we don't need to bother about whether there exist other variables where xn can converge, because the convergence is unique. So we are done with that. Now let us concentrate on proof one by one. So first let us prove only if part. Now only if part means we assume that it converges in mean. That means xn converges to x in mean, that is L1 converges holds, which means that expectation of mod xn minus x goes to 0. And by the previous lemma, it immediately implies that expectation of mod x is less than infinity. That means it is integrable. Now all we have to show that xn converges to x in L1 or in mean. This will imply that the sequence xn is uniformly integrable. This we have to show. Now clearly supremum over n expectation of mod xn less than equals to supremum over n expectation of mod xn minus x plus expectation of mod x just using triangle inequality and taking supremum, the last part, the supremum doesn't hold because there is no n, so it is just expectation of mod x. And again, since xn converges to x in L1 and by lemma expectation of mod x less than infinity, so it immediately says that supremum of expectation of mod xn less than infinity. So actually we have to show that this sequence is uniformly integrable, so we are slowly approaching towards showing the conditions of uniform integrability. Now you take epsilon greater than 0, then for any set A belonging to the script B, there is a sigma field generated by the class of subsets of omega. We consider such A such that probability of A less than delta for arbitrarily small positive quantity, and for n greater than equals to 1 we use the triangle inequality again, so that we can get integration mod xn dp over A less than equals to integration mod xn minus x dp over A plus integration mod x dp over A. Now we know that xn converges to x in L1, so integration mod xn minus x dp over A is less than epsilon. So this left hand side becomes less than epsilon plus integration mod x dp over A. But again, integration mod x is less than infinity, we have just proved it. So this whole quantity is again less than 2 epsilon, that means we call it epsilon star. So we have integration of mod xn dp over A is less than epsilon star. Again, epsilon star is nothing but 2 epsilon, so it is arbitrarily small and positive if n greater than equals to n naught and probability of A less than delta. So because we are considering this convergence of xn to x, and naturally this holds, we can think of convergence for a large num n and larger than n. That means we can find an n naught depending on maybe epsilon and maybe on delta, so that this condition integration mod xn dp over A less than epsilon star will hold, provided whenever n greater than equals to n naught and probability of A less than delta. Also, since we know that expectation of mod xn less than infinity, we can immediately have integration over xn dp over A less than epsilon n for a fixed n greater than equals to 1 and probability of A less than delta over the same set on which we are playing the whole thing. Now, so we have a number of epsilons, like up to n naught we can have epsilon 1, epsilon 2 up to epsilon n naught minus 1, and from n naught onwards we can have only one epsilon star. So let us consider another epsilon naught, a defined epsilon naught such that which is the maximum of epsilon 1, epsilon 2, epsilon n naught minus 1 and epsilon star. Now this set is a finite set, it has only n naught number of points, so we can find the maximum of this set, and which is again very small. Then for every n greater than equals to 1, integration over A mod xn dp is less than epsilon naught. So which in effect shows that since this condition, that is integration mod xn dp over A less than epsilon naught, holds for every n greater than equals to 1, and the right hand side is completely independent of n, because we have chosen epsilon naught to be the maximum of epsilon 1 to epsilon n naught minus 1 and epsilon star. That means right hand side is independent of n, but left hand side depends on n, so that we can easily take supremum on the left hand side and it has no effect on the right hand side, because as I have already mentioned, this is completely independent of n. So we have supremum over n integration mod xn dp over A less than epsilon naught if A belongs to script B, which is actually the condition, and probability of A less than delta. So this proves the uniform integrability, because it satisfies the conditions of uniform integrability, and hence we can immediately say, if we assume that L1 convergence, we can show that the sequence is uniformly integrable. Now if part, that means we assume that xn is uniformly integrable, all we have to show that xn converges to x in L1 or in mean. So, since we assume xn is a sequence of uniformly integrable random variables, we can immediately have from the definition and from the subsequent results that expectation of mod xn less than equals to c, which is less than infinity. That means there exists some finite c such that expectation of mod xn less than equals to c. And remember, right hand side c is independent of n. Again, it is given that xn converges to x in probability. So, we know that there is a result, there exists a subsequence xnk such that mod xnk goes to mod x almost surely. That means, although probability convergence does not necessarily imply almost sure convergence, but it will imply that there we can find a subsequence, may not be the whole sequence, but a subsequence, a particular subsequence denoted by xnk such that this mod xnk goes to mod x almost surely. Now, we apply Fatou's lemma, the old Fatou's lemma here to see that expectation of mod x equals to expectation of lim inf k goes to infinity lim inf mod xnk, because if we take limit n goes to k goes to infinity of this subsequence and take expectation, that is nothing but expectation of mod xk. Now, in Fatou's lemma says that we can take this limit outside the expectation sign, but there is an inequality sign. So, this quantity is less than equals to limit in lim inf k goes to infinity expectation of mod x n k, and since expectation of mod xn less than equals to c, we can immediately write expectation of mod xnk is less than equals to c, and again this does not depend on k. So, this expectation of mod x is less than equals to c and c is less than infinity. So, this shows that x is integrable or expectation of mod x is finite. Now, choose one epsilon greater than 0, choose a delta greater than 0 and take a and take one particular once a belonging to the sigma field such that probability of a less than delta, then this will imply that integration over a mod x dp less than epsilon and also supremum over n integration mod x n dp over a less than epsilon. Then since we know that xn converges to x in probability, just by the definition of probability convergence, we can write probability mod xn minus x greater than epsilon is less than delta whenever small n is greater than some capital N which is considered to be large enough. Then again splitting a set by its part less than type less than some quantity and its complementary part using the same technique as we have already mentioned and used many times. Hence, we have expectation of mod xn minus x. Now, remember we are trying to show that xn converges to x in L1. That means, at the end we have to show that expectation of mod xn minus x goes to 0. So, we have to bring this expression somewhere, and here we first bring this expression expectation of mod xn minus x. And we will play with this result, with this expression using all our arguments just described now, which we described just now. So, expectation of modulus of xn minus x equals to integration over mod xn minus x dp over mod xn minus x less than equals to epsilon plus the same integral over the set mod xn minus x greater than epsilon. Now, again modulus of xn minus x, since the first term is on the set less than equals to epsilon, replace modulus of xn minus x by epsilon, so that there will be an inequality, and replacing this integral of dp over a smaller set by the whole by 1, we can have this entire quantity, or rather expectation of mod xn minus x less than equals to epsilon plus integral mod xn minus x greater than epsilon mod xn dp plus integral mod xn minus x greater than epsilon mod x dp. Now, just with the previous arguments, each of the last two terms is less than epsilon. So, eventually this entire quantity is less than 3 epsilon whenever we have small n greater than capital N, which is considered, which is already taken to be large enough. So all we have proved that expectation of mod xn minus x less than 3 epsilon for arbitrarily small epsilon whenever n greater than capital N, which actually implies that xn converges to x in L1 or xn converges to x in mean. So that actually proves the entire theorem, both if part and only if part, that is both necessary and sufficient part. Now let us consider one small consequence of this stated as another theorem. Let x1, x2, xn are IID random variables with expectation of mod x1 equals to c less than infinity. Then expectation of mod sn by n minus c goes to 0 as n goes to infinity. That is, which implies that sn by n converges to c in L1. So using the previous theorem, and I will use another theorem like Convergence strong law of large number to show that for a sequence of IID random variables with finite expectation, we can say that the average or Sn by n converges to a constant, converges to the same constant which is the expectation of mod x1 in L1. Now since the proof is very simple, since C is expectation of x1, C is expression of mod x1, we can write by Kolmogorov's strong law of large numbers for IID random variables that Sn by n goes to C almost surely. Now we only have to show that Sn is uniformly integrable. Just consider this expression, expectation of mod Sn by n, which is less than equals to I equals to 1 to n, expectation of mod xi by n equals to expectation of mod x1, because we know that xi's are all IID random variables and expectation of mod x1 is less than infinity, that is the given condition of the theorem. So this proves the first condition of uniform integrability, that is expectation of mod of Sn by n is finite, is less than infinity. So first condition of uniform integrability is satisfied. Now take another epsilon, take any epsilon greater than 0 and take n to be large enough such that integration over mod x1 greater than n mod x1 dp less than epsilon, because we have already given that expectation of mod x1 less than infinity, and from absolute continuity this follows immediately. Also, since xn's are IID random variables, we can write modulus of xn dp, integral of this quantity modulus of xn dp over a intersection mod xn greater than n is less than epsilon, because this a intersection modulus of xn greater than n is a subset of modulus of xn greater than n, and by the condition of identical distribution it immediately follows. Then for an a set A belonging to the sigma field such that probability of A less than delta, again putting delta equals to epsilon by capital N, we have integration modulus of xn dp over A equals to, again splitting this A by a particular set and its complement, that is integration mod xn dp over A intersection mod xn greater than n plus integration mod xn dp integration over A intersection mod xn less than equals to n. Clearly the first term is less than epsilon and the second term is less than equals to n into probability of A. So this means right hand side equals to epsilon plus n delta, which is equals to 2 epsilon. So all we have, integration mod xn dp over A is less than 2 epsilon. Hence for every n, now this is true for any n greater than equals to 1. So this is for every n integration mod Sn by n dp over A, we can split this modulus of Sn, that is summation xi, by as less than equals to summation of modulus of xi, and we have this left hand side, that is integration mod Sn by n dp over A less than equals to integration over mod x1 plus mod x2 plus dot dot mod xn by n dp over A. And since they are all identically distributed, it is, we can write immediately, this is exactly equals to integration over of mod xn dp over a, which is less than 2 epsilon. Just now we have shown this. That means basically this says that the second condition of uniform integrability is also satisfied. We have already shown the first condition is satisfied. So naturally, by the definition or the conditions of uniform integrability, we can immediately say that the sequence Sn by n is uniformly integrable, and this completes the proof. The very elegant proof of mean convergence theorem indicates or explores the relation between two types of convergence, and it is clear that in many cases we can always find whether a sequence of random variable convergence in probability or maybe convergence almost surely. And on the other hand, we might have some idea about the expectation or the mean of the sequence of random variables and also the expectation of the limiting random variable. But how to put all this into one frame? Only one thing that we need is uniform integrability of the sequence of random variables. So this mean convergence theorem, as we have already seen, actually gives us a very nice weapon so that we can deal with all these types of convergence coupled with the concept of uniform integrability. So basically everything is very nice, but there might be some lacuna. So when you put this uniform integrability, or if a sequence of random variable that is uniformly integrable, that actually fills the gap in this entire paradigm. So in that sense, uniform integrability is a very nice concept, and later on you will see, rather we have already seen many examples, many cases where if we can prove that the particular sequence under study is uniformly integrable, then our entire job will be very easy. So you can easily explore some other limit theorem, some other types of convergence only using the fact that this sequence is uniformly integrable. So this concept is a very novel one, not a very difficult one, just involves the probability of the tail event, and based on that we can have really lot of things, lot of nice and beautiful things in the area of probability theory, especially in the area of limit theorems in probability theory.